Okay, so we've got here yet another Lynx. This one has some potential power issues. So let's just take a look at the notes that's come with it. It's basically a guy on Discord with an Atari Lynx 2. We'll start with the problems. Basically says the console worked to purchase, opened, cleaned. It's had some recaps, had a Zener diode replaced, D13, a resistor, R74, both transistors. Upon connecting the DC power, it would not boot, however, worked flawlessly on batteries and injecting 5 volts into C41. And C41 is just basically the battery spring. There's no real difference there. The switching happens on the ground, not the positive, so we just injected 5 volts to the positive rail. Reflowed the DC barrel, it allowed it to turn on, but the screen displayed black, white, or garbled image. Contrast wheel didn't work. Tried injecting to C41, and now the same thing happens on the batteries. So it seems like there's something gone wrong on the power rail. So when there's ever an issue like this, in terms of power rail, I won't use the normal plug. I want to monitor for current draw. So instead of, I just take my bench power supply and I'm going to limit the current to 1 amp for now. Because if there is a short, then we don't want things to go wrong. I've attached a ground wire to the shield. So this is the ground after turn on. So this will bypass all of this power up circuitry regardless, and just inject 5 volts into the system, which will fully boot, or should fully boot. And I'm just going to connect the 5 volt rail. And yeah, we have basically a dead short. So in this instance, I'm going to pull out the thermal camera, and let's just have a look at where that short is absorbing power, and that should pretty much point to the place to start looking at. So if we take a look at the Atari Lynx now, and I'll connect up the 5 volt power. And we can see nice and clearly there, that is the Susie chip, and that chip is now 40 degrees already. So without a doubt, the issue there is the Susie chip. If we take a closer look, you can see it's literally center of the die. So it's not like it's a trace, around, or maybe a short on the legs. It does look like a literal short inside the die. So it looks like the Susie chip is basically done for. So next up, let's just disconnect that. And the obvious answer then is we can't really proceed any further without swapping the Susie chip. But before we go and put a new one on there, let's do some basic tests, because the only way this chip would normally die is potentially some overvoltage. There's been some stuff replaced on this circuit here as well, and there's a few critical components in there that I'm a bit concerned about. So if we take a look at the schematic, and here's the power circuit. So power comes in, I've done a whole video on this circuit, but in short, battery comes through here, goes along, and this then goes through D13, which was replaced, through the Zener diode, and also through R74. So effectively, it's a really poor man way of regulating 5 volts from 9. This Zener diode takes all the brunt, and it kind of pulses on and off through this Q6. So I'm not a massive fan of this circuit design, but the key here is this has been altered, D13. If this is wrong, if this isn't a Zener diode and it's the wrong voltage, you'll instantly overvolt the whole system. If there's a short on this, just the same, you'll kind of pass the wrong current through. So my concern is maybe this has been overvolted. So let's just do some basic checks. The DC barrel, as you can see, the only difference between DC barrel and battery is that the battery negative comes in through L16, through the DC jack pin 3, and then out through pin 2, through L14 and onto the ground. When you put the DC barrel in, it disconnects pin 3, it lifts up, and pin 3 on the batteries is no longer joined, and the DC jack's voltage on pin 2 flows through. So the only difference between it working on battery and DC jack is literally L16 and the DC jack itself. So the issue there was probably just the spring in the DC jack. It wasn't joining pin 3 to 2, and that was probably the original problem, but now we clearly have a different problem. So I just want to test these two key components here for a start before we swap the chip and find there's another problem. So R74 and D13. So if we look on the board, we have D13 here and R74 here. So I've got the multimeter in diode mode, and if we touch them together, it beeps. So let's check D13 first, and that's not a good sign. Yeah, so this diode is shorting both ways. If we get another board, so this is just a donor, I think it's the donor off the last video, and we check D13, what should happen is one way with negative on the right side here, you get a voltage drop of like 0.3, and the other side you get a voltage drop, which is the Zener diode way, and it's 0.38 this way. When it's injecting a small amount of voltage, you just get a volts drop. So this would then, in theory, this should be shorting out when we connect power, because it would just simply pass to ground and dead short. So let's also check in resistance mode what R74 is doing, because this should be 120 ohm, and I can already see it says 30.0. So that's the wrong size for a start. So I'm slightly concerned there. So let's just measure R74, and we've got 30 ohm. And this is a 0-point crossing resistor that measures what the voltage is to set the level correct. So with that resistor off, it might not regulate correctly. If we measure the original R74 here, you should see it's meant to be 120. So this is a problem. This circuit will not work right. And if we put a new Susie on, this circuit's going to blow. So let's just fix a few things first. I'm just going to whip this diode off and make sure out of circuit. Is this diode blown, or is it a case of something on the circuit shorting? So that's the diode off. And this resistor is completely wrong. This needs to be 120. So let's just get that off for a start. I'll just get a 120 ohm resistor out of the 0603 resistor books that we sell that come with sort of every value resistor that you might need. Perfect for things like this. And let's just place that back over R74. Now let's just remeasure R74 to make sure that is now correctly 120 ohms. And now it is, so that's that one fixed. Now let's just measure this diode out of circuit. So back into diode mode, go on this side, and it's open. Go this way around, and it breaks down. So it's not actually that there's a fault on this diode, because it doesn't break down both ways there. So the fault, I presume, is on this circuit. You can see we get 0.1 breakdown there, and 0.1 breakdown there. So the fault is still on this circuit, and it's likely to do with things that have been replaced. So this is going to be a hunt for what's gone wrong here. You can see in resistance mode, we're getting 130 ohms over this diode. We compare that with a working board, you're getting 370. So even just off a basic resistance mode, something's not quite right. So before we diagnose any further, we know the Susie chip's bad. So let's just take that off. It could be interfering with all these lines. We'll just desolder wick this as well, and then if we're going to put a new chip back on this time, I think instead of hot air, we will try the soldering iron approach. The last one we did, we basically hot aired straight on. So it'd be nice to show the different way of soldering the chip on, which would be to simply remove all the excess solder off these pads and solder a new one on using your soldering iron instead of hot air. That's that cleaned for now. Get the flux off while it's hot. And with that Susie off, let's just remeasure the resistance over the diode. And you can see now we're back to 312, which is roughly within range of what the working board shows. So pretty confident that is completely dead. With the diode back on, if we chuck him back on, we should hopefully have a working power system. So to check that, I'll just put the meter into ammeter mode, and let's just go on the ground here, connect the bench supply to our multimeter, and now we can tap on to inject 5 volts here with the multimeter and see the current draw. And you can see now we get 130 milliamps current draw, which is more correct. And if we just grab, funnily enough, this previously working board with exactly the same kind of thing, no Susie chip because it was used as a donor, we should get a very accurate representation of if that current draw is within the right range for this exact same setup. It's literally same console, same revision, same chips missing. So it's a really good candidate for this kind of check. So we have the ground selected to the shield, inject 5 volts, and you can see identical power draw. So I'm pretty confident that circuit's now working. And if we really wanted to check, we can grip on the actual ground and inject 5 volts. And because U6 is connected to the cartridge connector, which the game shorts out, you can see if you go to the Lynx and the power circuit, I've now done a whole new article for this. You'll see that this circuit here, the 5 volts in comes through the cartridge connector, and then when you insert a cartridge, it joins through this yellow pin, goes through, and powers U6, which is this chip here, which is a hex inverter, which ultimately controls this Q12 transistor, which is where the ground is switched to turn on. So U6 is here, where it gets the power from the game cartridge being inserted. It's also over here. So when this gets power, it feeds through all these inverters, which finally, this inverter here drives the gate. So U6 on channel D drives the gate, or the base of this transistor, and that turns ground on. So without a game in, that won't be able to work. However, if we simply short pin 31 and 33, which is what the wiki will also tell you, or simply put a game in, one or the other, then we should be able to get it to power on. So for now, I've just chucked a game in, and let's do that test again. Ground on here, 5 volts on here, and then short TP17 to TP18. And you can see it powers on to the 130 milliamps. So now we know it's turning on. Let's just connect it straight up to the bench without going through the multimeter. So if we do that same test on a working board, if we were to just probe here, I've put 9 volts to this because I know it works, and test on the cartridge pin, you can see it scares you and shows you 9 volts. Now remember, this is not the ground that the system sees. It goes through Q12 and it's regulated down. So we have to move the ground here to the system's ground, which is, say, over here, one of the shields, any of these shield connectors, and we'll remeasure the cartridge pin. You can see it's then showing 5 volts. So it's important to prove the way you think you're measuring a circuit correctly on a working board. We can see that we have to go on the system's ground over here, not the battery spring. So even though the battery spring has 9 volts going in, if we go to system potential over here, you can see the system only sees 5 volts, which is correct. So now we know we are testing correctly and not incorrectly. Let's bring back the customer's board. Lower the volts down again, just for testing, to 5.5 volts first. Connect up to the battery springs. Power on the system, TP17 to 18. And keep forgetting to put a game in. So in fact, so I don't keep forgetting to put the game in, this is why I like to do this. Just bridge pin 33 and 31 together. And then you never have to have a game in to get a power on. So now we have that bridged, which means U6 on the power on circuit will always receive power. We can now stop trying to remember to put a game in. Just put that 5.5 volts back on. Juice up TP17 to 18, which now turns on. And if we measure again, here first, you can see I've just put 5.5 volts in. The circuit, however, the main system, you can still see is actually seeing 5.5 volts. So this power circuit is not working and is not safe still. You can see from there it's not safe. From here it's not safe. It's seeing the actual system's voltage and not the lower voltage. So let's just do some basics again. Let's just take a diode off the known working system and swap it over. So I'm just going to take this suspect diode off because it's a new one. Use this diode from here. And we can test again. So if we'd have just gone ahead and put a Susie chip on here and powered up with 9 volts again, everything would have just shorted. And in fact, I'm overlooking something very simple here. Well, a check rather, that's very simple. Let's just make sure that in continuity mode, that the battery's ground isn't shorted to the system ground. And it isn't shorted, it's 480 ohms, because otherwise you're not going to get your correct, system where the ground side of the system is what loses the voltage. So let's just check a working board. And you can see roughly the same, so it isn't that. That was worth a quick check. So same again now, it's cooled down. Connect 5.5 volts to the actual battery spring. power on, and I can see the power draw has dropped already. Go to the system ground, probe the battery spring, put the multimeter into voltage mode would help, measure the output system voltage, and there we go. So now we're getting it right, which means one of the most crucial components on the board, this diode, is wrong or dead, or maybe was just installed backwards by the user. So a Zener diode on the schematic is meant to be the line side facing R74. So simple check for that. Continuity mode on the multimeter. And if we now take the board with it removed and measure R74, you can see R74 is here. So ground side should be here, the line, and it was installed that way. So we simply have a case of a faulty diode. So this diode's no good. So I'm finally confident in the power up sequence now. So the whole power circuit, that I'm going to connect this up, 5.5 volts. Turn it on. Measure the system voltage, and you can see it is 4.8. I'm going to increase the voltage on the input to 6 volts. Measure again. You can see it's the same. Go straight to 9 volts, which is what the system would expect. And you can see we get the same. So now we are correctly powered up. We are safe to go from here. The DC power jack would have no difference than battery. So while we're at it, let's just check now if a DC barrel will correctly work. And if we take a look at the schematic, the DC jack now should have disconnected pins 2 and 3, so the battery ground is no longer connected, but ultimately the ground that we know. So the spring itself here is disconnected, so we can't use the spring anymore, but pin 2 of the jack goes to L14, comes through to D10 on the non-line side, and you can see the positive still comes through and goes to the battery spring. So positive battery spring, but to the positive of D10 for your ground. So on the multimeter now, we're in volts mode. Positive can be positive here, but negative needs to be the positive of D10. And you can see there we get the input of 12 volts off the jack. Now to power up the system. And we can't see the current draw because we're off a DC power. But if we measure here now, you can see we've got 5 volts. So system's fully good, totally safe now to chuck a new Susie on. So let's do that next. So I've got a Susie here off one of the boards I have lying around. No idea whether it works. It's already a donor for other parts, but I'm going to make a presumption it works. And we'll soon find out when we connect it all up. So to do this, I'm going to try and solder this down. So we want solder flux. And we use Solder King. We sell this with the official UK distributor for Solder King. It's like Amtex, only cheaper and easier to get genuine because every batch is made for us directly in the UK. So we know exactly what we're getting. And then what I'm going to do is pre-tin one of the pads here with a bit of solder. Bring in the Susie chip and line this up by eye. Once you're happy with one position, tack the next position. So I'm just going to tack this corner. And try to go opposite corners and just nudge the chip into the exact position where you're happy that all the sides line up, and don't commit to this until you're happy all the sides line up. Once you've done that, it's as simple as drag soldering down, plenty of solder. Don't go the sides where you've just tacked, so don't go here or here, otherwise it's going to come straight loose again. So I'm going to start at this corner. Plenty of solder, can't have too much. And just go down nice and slow on the pins, applying plenty of solder flux as we go. And with that all done, they look all good to me now. Just clean up the chip. So now let's do the power on test. Let's just connect the 9 volts to the battery. We want a speaker in to see if we can hear the game load. I've got the chips game in. Volume midway. Turn on. You can hear the speaker pop as we do that, so we know it's kind of turned on. Power draw is a little bit low. It's like 88. And we're getting no audio at all. Let's flip this over carefully while it's still on. And let's just grip on ground, and let's take a look at what the Hayato is doing. We have 5 volts, 5 volts, nothing. And if we go to the LCD circuit here, you can see we should have 5 volts and 5 volts. This is a typo here. I'll just recorrect that bit after. The third pin should be the pulse of the square sine wave, and this is the thing that drives the contrast circuit. It comes from the Hayato. Then we should have a bunch of clocks all running on the Hayato. So all these lanes should be a bunch of clocks, and we're getting absolutely nothing. So my suspicion is, even if there was something wrong with the Susie, the Hayato chip, as long as the Susie's in, the Hayato chip would be running. And we're getting nothing everywhere. Absolutely nothing. So the fact that also we suspect the Susie and the whole circuit was injected with far too much voltage, mainly because R74 was wrong and D13 was bad, we're probably looking at a dead Hayato as well here. So let me just probe that we're getting like a crystal. So you can see you got your clock. So the clock is going into the Hayato, but the Hayato is doing nothing at all. There's no activity on anything. Just everything about the Hayato is doing nothing. You can see it's just basically what's looking like a dead chip. It's not generating heat, but it's also not doing anything. So as a last resort, a very last resort to presuming the Hayato is dead, let's chuck on the Susie that worked on the last repair but without visible screen. So the game loaded, but we didn't have screen output. So we know this will load games. So let's just take this one off and put that one on, and then we'll test again. So this one works. We will get game audio, and we'll get the Hayato responding. We just won't get any visual screen. But that will tell us if at least the Hayato on this board is good. Because if it's not, then there's absolutely no point in continuing with this repair, because it's basically 2 ASICs, which you might as well then just get another board. It'd be the cost of another board to do the work. And I would definitely recommend hot airing these on. The soldering took longer, you have to get bridges off, and the kind of layout of them pins does not lend itself well to doing soldering. So my personal preference after trying both is just hot air these chips on and off. And we just got to let this board cool. So that's quite a lot of hot air on. The last thing you want to do is power these boards up while it's still hot, because they could then short out and die. So we'll give this plenty of time to cool off. And just while the board's warm, just cleaning any residual flux from everywhere, because flux comes off much easier when it's warm. And there's no point connecting the screen in this case, because we know it won't work with this Susie. We can do that after if we feel like it and we get audio. But the main thing we'll do is turn it on, check power draws, and probe the LCD pins as well. If you can't hold your hand over the chip for a few seconds, then it's still too hot. Once it's at the point where you can just hold your fingers on and it doesn't burn, you're cool enough to, juice up the board. So that's 9 volts in. Juice up the console. And this is a known working Susie, as we mentioned. Power draw looks the same. Not seeing any fluctuations. So I've got a suspicion this is still doing absolutely nothing. So let's just flip over carefully. And let's just probe again the LCD pins, which is the Hayato running and driving. And you can see still absolutely nothing. So this is unfortunately not only a dead Susie, but a dead Hayato as well. The likelihood was, because the power circuit was faulty and then received 9 volts, it's wiped out probably everything on the system. Your RAM's probably dead, the shifter's dead, the ASICs are dead. We've now fixed that and they correctly get 5 volts. But the problem is this has already received 9 volts and maybe it's been overdriven and simply died completely. Yep, and I can just double check the systems are definitely getting the 5 volts. So this board's now repaired in the sense of all the power circuit's fixed and it boots, but the likelihood is this is blown, this is the wrong one, so I'll give the customer his back and leave it off. But I reckon the Hayato and the Susie are dead, probably the RAMs are dead, and then you might have level shifters. So I'd personally not attempt to repair this board. But hopefully you've seen how to at least fix the power board, how to detect a short, and you've learned something from this. This is what I'd call beyond economical repair. Even if I swap the Hayato, I reckon the RAM's dead as well. Then you're swapping RAM, and then these are dead. And then most passives should work, but then you could have this dead, you could have the amps dead. There's so much that could have blown with having the wrong voltage through it. So in this instance, I'd probably keep it for this side of the board, the high voltage side and the power rail side, and donor this side. So that's it for this one, guys. I hope you learned something, and I'll catch you in the next.